fire in your garage. And then you will actually need to access to the folder to copy the mesh file. Okay, so just now the IT guy has mentioned that only 25 of the workstation can access to this folder at the same time. So basically you will need to create the folder at your local machines and then copy the file from that folder batch by batch. Don't copy at the same time, okay? Okay, then for 9th October, right, we will actually cover the fluid structure interactions kind of simulations, which we call it as FSI, and then we will follow by the small student projects later on 9th October. So, firstly, maybe I think Prof. Victor has already mentioned what is CFD. So maybe let me give a quick overview on it again. So basically CFD stands for computational fluid dynamics, and it's actually a tool, or we can call it as a calculator for engineers to predict the fluid flow, heat and mass transfer, chemical reactions and related phenomena. And so for actually the CFD solver can solve for like aerodynamic forces, heat transfer, particle flow and etc. kind of applications. And in order to predict these phenomena, right, basically the CFD solver solves like the conservation of mass, momentum and energy equations. So if you want to solve more about other variables, right, like example aeroacoustic, particle traveling kind of things, then we will need to solve additional equations. Like for aeroacoustic, right, we will solve the light field equations. Okay, so the main purpose of using CFD is like for conceptual study of a new design or detailed product developments, optimizations. Like example, you have a product that is actually not optimized enough, so the engineer can actually use these CFD tools to improve the performance. And also it can use for troubleshooting, like example, there are some defect in the products, then the people want to troubleshoot why this, how and where the software error is coming from. Okay, and also can use for redesign after the troubleshooting. So you guys cannot see the video. Okay, these are some of the applications that CFD can do. The first one is like the internal combustion engine, where you see the cylinder is actually moving, and then the air particle is actually, after the combustion, the exhaust gas will be released from this tube. Okay. And then this is the other applications, like flow over disc brakes, some things. Okay. So how does CFD works? Actually, I think Prof. Victor has already mentioned already quite detailedly already. So basically, CFD solver is solving the problem based on the finite volume methods. It means it actually break down a very big control volume, or we call it as fluid volumes, into a lot of smaller volumes, and then all of these smaller volumes, that it will solve it, solving the equations and get all the variables that you need, like the pressure, velocity, temperature, and etc. So the general procedure is like we will need to have the CAD model first. We need as example for this case is your pipes. Okay, so after you get the pipe, you need to split this big volume into a lot small volumes, then we call it as meshing. Okay, so after the meshing, we will so-called send this mesh to the solvers, and the solvers will solve the equations and give you the results. Okay, so just now I actually had mentioned that there is a free student version that is available for all the students. So basically you can go to this nsys.com/student. Maybe you guys need to want to copy it down. Copy down already.
Download already.
Download already so far. Very efficient. Nothing?
Very little.
Yeah, actually there is a max limitations. So if your FYP is the project is small, then you can use this. If not, you have to come back to this lab to use the facility here. Okay, so basically you can just go to the nsys.com/student, this website, and then click on the free downloads. So you just need to click agree and then download the software package and the license key. And then after that you have to follow the instructions to install the software. Okay? It's okay for you guys? Okay, so next maybe we'll proceed to the demo.
Who has this side attention? This side is.
Okay, so for the demo, right, basically all the procedure and step is like already included in this handout. So if you guys have missed the step or something, you can always refer to this handout. Okay, so the first demo for today will be on flow over 3D cubes. So maybe let me do the simulation first, then you guys just listen to me. Then after that, you guys can like so-called do it on your own again. Okay. Okay, so firstly, whenever we want to do any simulation, right, for ANSYS, we will launch this Workbench 16.1. For your case, it's 16.2, which is the latest version. So after you have launched the Workbench, right, basically you can solve all the solvers which is on the left. So basically you can do the fluid flow analysis, structural analysis, and even electromagnetic analysis with ANSYS. And then all of this can be coupled together to perform multi-physical analysis, like fluid structure interaction is one of them. Like it's actually coupling the fluid solvers and the, it's a bit slow, structural solvers. So basically they share the information of geometry and the result, which is fluid pressures, together from the fluid solvers to your static structures. So this is a simple one-way kind of fluid structure interaction. So if we want to conduct those two-way FSI kind of so-called analysis, right, then you will need to use the transient structural instead of static structures, and you have to add in one more system couplings modules to allow these solvers to talk to each other in real time. Okay. So for this particular FSI, FSI, we covered it on the second day of trainings. Okay, so firstly, for the flow over 3D cube, right, we only need one solver, which is the Fluence only, and basically there are another solver which is CFX. It's another very powerful CFD software, but we will not touch on it for this 2 days workshop. And okay, so maybe let's start from the geometry first, because as mentioned just now in the slides, right, the procedure is like firstly get the geometry. It's either you get the geometry from your other colleagues or you draw it yourself. So mainly for the industry, right, the engineer will normally like split into two groups. The draftman get the drawing, then the CFD engineer will get the drawing from your colleagues and then imports to this ANSYS and then do some touch up. Because for the geometry that is very complicated, right, those small features might not be needed in your simulation. So if we import purely just from the geometry that is prepared by your colleagues, those small features, if you need to resolve it, you need to have a lot of fine mesh around these small features. More mesh represent we have to get more time to solve it. So basically it is inefficient. Okay, so maybe after you get the geometry, you have to do some so-called geometry preparations. Then after that, go to extract the fluid volume, because if you are doing CFD, right, the structure itself is not the objective of your project. So maybe example, if you want to do a flow simulation within these rooms, so basically if you get the whole drawings and including computer and everything, so firstly what we will need to do, we have to remove all the small features, like the mouth is not important, right, we have to remove it, and then the computer maybe we can use a simpler blocks to represent and only those small buttons. And after that, we have to extract the fluid volume, meaning use a big volume to minus away all these small features, because this small feature is not needed, because structural kind of simulation is handled by another solver, which is the our static structural solver here, or transit structural solver, which we call it ANSYS Mechanical. So after we extract the volumes, right, then we have to do the meshing. So maybe let's start with the geometry first. Okay, so there are some guidelines on how to create the geometry, or we call it fluid volume, for the external aerodynamic kind of analysis. Okay, so for external aerodynamic, right, if for example you have a object here, so you have to create a fluid volume to enclose this particular model, right? If for example this is the car, right, then we have to make a big fluid volume and enclose it. So basically this is your fluid that you are interested in studying, and then these things will actually subtract it off. That's only the hollow kind of volume. Okay, so there are some guidelines to dimension the so-called fluid volume. So if this is your length, this is your height, right? So in front we must have enough space to let the flow to stabilize. So this must be 5 times your length. Then downstream, if you need to observe those processes at the back for the downstream, right, you need to have enough volume to study this also. So this length is about 10 times of your length. Okay, so for this right, it's about 5 times of your height. So this is the general guideline for external aerodynamics. So any of you is doing this kind of analysis, like external aerodynamics. Okay, so I will start with creating the block first. So maybe let's use the XY plane as a base plane to do the sketchings for this particular block. Okay, so please look at, then go to sketching. You guys don't need to follow, just so-called listen to me. So draw a rectangle from here. And then after that, because we have to give dimension in order to so-called provide the correct dimension information. H is 2 meter, V is 1 meter. Okay, after that, we will need to extrude the sketch by 1 meter. Okay, then generate. So have you guys used SolidWorks or other CAD models before? Actually, this particular design modelers is for CAD preparations, or you can actually import the geometry, which is AutoCAD file, Creo, SolidWorks, or even those native formats like IGS, stat files, and etc. Blah blah blah. Okay. So in another way, it's like you have the draft, right? You can actually draw the 3D drawing by yourself in this design modeler instead of using SolidWorks or others. Okay, so after you have extrude this, right, what is the next step? So I've mentioned just now that we need actually the fluid volume. So basically, when you study the CFD, means you are studying on the fluids, not the structures. Okay, so next thing, we will need to offset the planes. Okay, so we offset it downward to okay. So maybe here is the base flange, right? And this is the edge. So 5 edge is we have to offset this plane by 5 meters. Okay. So offset global Z by -5, then generate. So you can see your plan is actually offset. And the next plan 4. So from these plans, right, we need to create another sketch that can enclose these so-called small models here. Okay, so let's go to the sketching again, and then create a big rectangle. Okay, so as mentioned just now, right, we have to dimension it based on the guideline. So let's dimension it. So from here to here, so far, here. Okay, so what should be the distance from here to here and here to here? So it's about 5h, right? So 5h is basically just 5. Okay. So L1 and L2 is 5. Okay, so basically this length should be longer because it includes the so-called your models here, so should be how much? 6, right? Okay, so this seems to be like the center already. Okay, then L4 is 3 to 5 times of the length. So meaning maybe let's use 5 times of the length. 5 times 2 is 10. And then L5, who can answer? 20, right? Okay, then next we have to extrude this. Okay, so this is the sketch that we want to extrude, and we have to add additional volumes to it, but not so-called merge these particular volumes to these volumes, then end up we have only one big rectangular box. Okay, so we have to extrude about what is the dimension? Basically, tens, right? Okay, so just a rough value.
Do you understand what is trying to do? Yes. Yes. Okay, so you see, let's say I just want to reinforce what you're trying to do. Okay, when we talk about external flow, right? Let's say this is a body. Okay, that means it can be whatever you're doing. It's a flow. I want to see how does the flow go over this body. Understand? So this is called external flow. If I work on an air fryer, let's say I got a cylinder here. Okay, I want to see what's inside this cylinder, right? It's called internal flow. Because I'm putting my air in, right? I will see these things here. So it's called internal flow. Okay, so this is a solution domain, but this is also a geometry. Okay, because I solved with this initial thing. Now if I have an external flow, right, I need to have a solution domain. So that's why we did that just now. Okay, you have a body, you have a solution domain. This 5 meters, right, or 5 times, right, is a guideline to you. Okay, basically what you're trying to say to you, right, is that you need to give some thought to how you do your solution domain. You cannot just say, I'll just do the figures I want to do, 30 meters, 20 meters. Yeah, you understand? It cannot be the shortest road, it cannot be 1 meter, 1 meter. You understand? So there must be certain guideline. And you do your literature review, right? People will tell you, say, I do 5 times the back of the, for the back, I do 5 times the length of this, or 10 times, for example. So they are all values that people have done and they have researched on. Okay? So when you want to do a flow that's external, right? What you need to do actually is to do the meshing, right? Outside of the body. Yeah? So actually this is the meshing that I'm doing. You all see? Okay, so the body, right, because it's external flow, right, I don't mesh the body at all. So at the end of the day, right, this is how my mesh will look like. This is how your mesh will look like. So what does your CFD code see, right? Your CFD code doesn't see this model at all. The CFD code see the meshes around the model. Understand? And every mesh, right, I solve one equation. Understand? Okay? So because it's external flow, right, there's a boundary layer. So I need to make sure my mesh, right, is properly designed. So it's very fine here, then it expand out. Okay? So some students can also say, why not I just mesh the whole thing fine? You can do that, but then you take longer time than somebody else who doesn't do that. Okay? So that means you can take 2 days to run the simulation, your friend can take 2 hours to run the simulation. Both will be the same result. Okay, the one that 2 hours, right, because there's a better mesh design. Yes, not true. Understand what I'm saying? Okay? So this is how you do, this is called the solution domain. This is called your geometry. Okay, this is your geometry. Yeah? But in this case, right, your meshing is all inside the geometry. Correct? So your solution domain is called your geometry. Because it's the whole thing, it's the same thing, it's the internal flow.
Okay, so next, as explained by Victor, we have the geometry and the control volumes now. So what we need to do is to subtract these big volumes to this small volume in order to get what is shown there, which is a hollow kind of volumes. So we have to use the subtract functions. The target body is the big one, then the 2 bodies is your small body, then click generate. So from now on you have 1 solid models which is hollow. Okay. So after this step we can just simply close this modeler and then the file will be automatically transferred to the mesher. So you can see a green tick here, which means your geometry models is ready for use. So the next step is to do the meshing. So we just need to double click on this mesh, and the mesh will actually automatically read the geometry from the previous step. Okay, so just now Prof. Victor had mentioned about we have 2 types of mesh, right? One is structured mesh, the other is unstructured mesh. So why researchers want to do structured kind of meshes? Because while doing the solving, right, it is much faster as compared to the solver to solve to unstructured mesh. However, if you the formations of the mesh will be the other way around, meaning it's more difficult to build the structured mesh rather than the unstructured mesh. So, but for the commercial software, right? Okay. Yes, okay. So for commercial software, we normally will use the unstructured mesh because it is easier to build. So Christian name, right? Okay. Christian send me an email. Okay. Okay. So basically, for these particular meshes, we are allowed to do the meshing in like automatic kind of way. Means we just need to control the overall sizings, means like change all to 5 or something. Okay, so basically this relevant center is to control the overall mesh size in this domain. So if you click 5, right, the mesh will be final. And then the smoothing and transition means like from one cell to another. So normally we will like near to the wall or object, we will have a so-called final mesh. And then away from the wall, it will have a coarser mesh because normally at the wall region is the most important region for people to resolve it and get the physics inside. And the other way is like we can insert the inflations layers to get so-called the boundary layer to be resolved. Okay, so how to compute the inflation layer? Firstly, you have to click on the geometry, and then select the faces which is like involved for your inflation area. So basically, it's the 6 faces of your block. Okay, but not including the big block. Okay. So let's go back to the mesh. So there's actually an advanced size functions, meaning you can actually allow the meshes to like go and see where is the curved surface, and it will automatically so-called refine it. And the other is proximity, means like normally when you have a gap between 2 objects, right, you want to create a mesh on it. Definitely the mesh size should be smaller as compared to the surroundings areas. So this function allows the mesher to automatically go and find where are the small gaps and so-called refine the mesh. But for this case, right, we are only having 1 big block and 1 small block, so it's not necessary. Okay, so let's try to mesh it first. Okay, so you think this mesh is good enough? So maybe you can okay, so you see the boundary layers actually formed here. That is away from your blocks in order to resolve the boundary layer kind of physics. And then away from it is the meshes, which is coarser mesh. Okay. However, you can see right from the boundary layer direct, I mean the mesh right after the boundary layer is like having a very big transition. Means from one side expand suddenly to very huge mesh. So this is not a very good kind of settings. Okay. So maybe we have to refine the setting, and it actually takes time now. So maybe we will just stick on this kind of mesh for the simulations. Okay. Okay, so after we do the meshing, right, we have to name, like tell the solver what surfaces belong to wall and which surfaces belongs to your models. So how to do this? Actually, we can just so-called select on here. So if example like this is actually within the wind tunnels, so we can just name this as wall. And this is the inlet, and this will be the outlet.
You know what it's trying to do? What it's trying to do, right, is that my flow is going from here to here, right? Where do I set my inlet? That is the flow where it starts, right? It's not here. This is where you set your inlet. Okay, so this is called your push your edge. Okay, so in physics, right, there's this thing called the mass flow in, because of mass flow out. Okay, whatever you push it in, right, it has to come out somewhere. This is your mass out. Alright, so this is called outlet. Right? If you're doing a 360 degrees, for example, kind of thing, right, you can put it as periodic condition. Alright, but if it's a wall, right, let's say a wind tunnel, right, then we say this is our wall. Maybe it's like a roof. I think where we are. Understand? For this case, right, it is an internal progress my inlet. It will be on this plane. Yeah, this is where I've set my inlet. Okay, then this maybe is my outlet, or I got a tube here, right, I say it's my outlet. You cannot put a CFD simulation, right, you only have inlet, but there's no outlet. Very hard to do, you always have damage. Understand what I'm saying? Okay, so that's how you do your constitution. Just now we talk about meshing also. In meshing, right, we say that these three things are fine, medium, and coarse. Very simple, right? But actually they're very hard to achieve. Because right, my coarse definition and your coarse definition might not be the same. Yeah? So there's a way to quantify what's a fine mesh and the coarse mesh and the medium mesh. And then with these three, right, we call this as the grid convergence test. Okay, that means right, we will do a certain test. Let's say I got a certain mesh, let's say for a rectangular box, right? This is my mesh. Okay, I do my result. Alright? Then I say, okay, the result's not very good. I think it's not very good because the results are not accurate. I double the size. Okay, so I got two columns now or two rows now. I do this mesh. Okay, I get some result. Okay, then I say, okay, maybe it's okay already, but let's try another one. Okay, I even further refine. Okay, then when I get the same result from this and this, right? Let me ask, which one will you use? This or this? Second one, correct. So to me, right, this is my fine mesh. Because to me, right, even though it seems like it's a medium mesh, right, but this result is as good as a fine mesh. This is my final mesh. Okay, I don't need to resolve it any further. Understand? Okay, so this is how we do our treatment. All of you must do this with common sense. You cannot just do your thesis right, say, I choose this mesh because I think this is the best mesh. You need to prove why this is the best mesh. Understand? And this is a test in okay? And this is called the grid convergence test. Alright? Okay.
Okay, so since we have already named the wall for these wind tunnels, inlet and outlets, so actually why I said this phase is inlet because normally for external aerodynamic, what is important is how does the vortex shedding kind of phenomenon have to be so-called captured. So meaning we have a shorter length from the upstream phase and longer length to the downstream. So this is outlets. And what we are missing here is the geometry itself. So this model maybe we can name it as a car. Okay, so now we have all the boundary conditions defined: wall, inlets, which is at the upstream, outlets to the downstream, and the car. Okay, so maybe for the mesh setting, right, maybe we can take a look. If we reduce this to cos, then what will happen? Okay, so you guys can see the difference, right? From very fine mesh to this coarse mesh. So shall we just try with the coarse mesh to do the calculation and then check what's the result? And then we compare with the fine mesh. Okay. So you will see a green tick here after the meshing is done. Then next is go to the setup for the solvers. So just now we have actually mentioned about the parallel processing, which you can actually set here. So if example, right, for your machine you have 4 cores, you can just simply type in 4 to utilize all the 4 cores in your workstations. And the option here, double precision, is actually to reduce the round-off errors. Okay, so maybe just activate it, click OK. Okay, so this is the interface for the fluence, and then on the left hand side here is actually the tree that is illustrates the general workflow for you. So we have to start doing the simulation from this setup and then all the way down to post processing, which is to extract the result. So first of all, go to the generals. We may check the mesh quality or even check whether it's the minimum volume is a negative volume or not. So basically, for safety analysis, you are not allowed to have any negative volume. Okay, so then the next thing is the solvers, pressure based, density based. So what is the difference for these two solvers? So examples, right? If you want to conduct those compressible flow kind of simulations, you have to use the density base. Okay, then time means you want to do steady or unsteady kind of simulations, and the gravitational is actually if you are considering the gravity kind of effects, right? You can define the gravitational acceleration directions in any of the components. Okay, so for this case we can just ignore it and do a steady state simulations with incompressible kind of solvers. Okay, so for the models, basically you can actually do a multi-phase flow. Like example, you have water and air, which is like open channel flow, or chemical reactions, and maybe missing kind of applications. So for the energy equations, when to turn it on? Basically, if we turn it on, right, the solver will solve the momentum equation and mass equations together with the energy equations for those applications on like thermal analysis. Okay, so if temperature, this variable is not important for you guys, you can just switch it off. Okay, for our case, right, basically we just need to find out what is the pressure and velocity distribution across this flow domain. So we can leave the energy equation off. And this is the viscous models where we have been talking a lot just now on like the range model, LAS model, and etc. So inviscid flow basically is like Bernoulli equations. Then laminar, if like you calculate the random numbers, right? If your flow regime is belong to laminar, you can just use these laminar models. And these these 1, 2, 3, 4, 5 equation is belong to range models. And then this is the so-called Reynolds 7 equations models, and this is the last eddy simulations models.
So do you remember just how I showed you the three things: RANS, LES, DNS? Okay, so basically you're just going to click the buttons here. You don't even write the equation. You just choose whatever you want to choose. You do a simulation. Yeah, but you need to analyze the results now. When you use a Spalart-Armaras, right, which is one equation, right? One equation meaning what? You're just only solving one equation, right? So it'll be very easy, very fast to get a result, right? But might not be very accurate. Then you move on to the second equation, 2 equation, 3 equation, 4 equation, 7 equations, right? The more equations you go to, right, the more you solve, okay, the better your results are, the more things you can get out of it, right? But then you need to understand even more of the solution and the Bernoulli equations, right? So it depends on whatever you want to do. But typically for FYP, right, we're looking at K epsilon, K omega, okay? Your SST, you'll use it also sometimes. Sometimes people start with Spalart-Armaras. So let's say you're doing a large body external flow, right? You're really using a Spalart-Armaras case. Okay.
Okay, so let's try the Spalart-Armaras models. And then, so is radiation important for this particular simulations? No, right? No radiation, because we never consider the thermal temperature kind of things. Is it a heat exchangers kind of simulation? No. So species transport, are we injecting particles into these models? No, right? So discrete phase also. Are there any solidification and meltings? No. Acoustic? No also, because it's purely aerodynamic kind of analysis. So we can just leave everything here as default. Okay, then for materials, basically if your target material is water, right, you can go to the Fluent database and then pour the materials out and copy so that you can save to your directory here. So for this case, right, we are actually doing airflow simulations across the body, so we can actually just stick to the defaults and then go to this cell zone conditions. This cell zone is basically this so-called the hollow volumes here. So you have to edit it to define what are the material that is being used. So for this case, it's air, and click OK. Then the next thing is to set up the boundary conditions. So just now we have named the surfaces already, right? So that will be read into this solver, and after read in, we have to define like what is car. Car is basically, we can treat it as a wall. Okay, so inlet is basically you can define it as velocity inlet, mass flow inlet, pressure inlet, or etc. So for this case, right, we will give a inlet velocity for this inlet. So how much you want to put? 5. Fine. Let's put 5. Okay. So when you activate the energy equations, right, you actually activate these tabs to enter the temperatures of your wall or something. Okay. So just click OK. Then the outlets. Normally we will define it as a pressure outlet to, like example, allow this so-called flow from upstream and downstream is discharged to atmosphere. So the gauge pressure is 0 and the operating pressure is 1 atm. Okay. So just click OK. Then double check is the wall belong to wall. And next is to so-called define the solution methods. So basically when we split the big volume to small volume, right, there are a lot of so-called methods for the discretizations. So we have simple, simplex, piezo, and couples. So maybe later on you guys can try like what's the difference across these few methods. So basically for simples, right, it's a default method. Then simplex is actually more suitable for those when you have a low quality mesh kind of control volumes. So then piezo and couple is for another features, but basically couple will achieve faster, but you need a finer mesh and also longer finer mesh, and is actually require higher memory for your simulations. Okay. So what is the first order and second order here? Basically, it's the solvers when you solve the like the computational methods, right? So when it is solving like the Taylor series, right? So basically you have first order and second order, and the higher order term. So for this case,
yeah, I want to show it to you what we have first order and second order is. When you do your simulation, right? Okay, when you differentiate ones, okay, normally it's called a first order differential equation. Okay, so I only do ones. But if d square y d square u dx square, right? Okay, you're doing a second order differential. Okay, so he said Taylor series, but actually whenever we do our simulation, right, it's called a Taylor series, right? It's also called a Maclaurin series. You all learned Maclaurin series before? Okay, what is Maclaurin is that we have a function of a fx. We can actually write this as fx plus f prime x over 1 factorial plus f2x over 2 factorial, so on and so forth. Okay, differentiate once, differentiate twice, differentiate 3 times, 4 times. Okay, so this is what you're trying to do. The higher order you go on, the more significant is your figure, right? That means the more accurate answer, right? But the longer, again, the longer you solve the equation, right? So for CIT, the normally what we do, right, is that we do a first order simulation first, so we reach convergence faster. Okay, once we stabilize the equation, right, in the solution, we change to second order to improve the accuracy. Okay, so it's a methodology, right? Okay, but sometimes, right, first order is good enough really, because when you're doing on a simple case, right, we're just looking at your u, v, w, the 3 velocities, right? You don't need to go to the second order, for example. But if you're looking at turbulence, right, where you have a u dash, v dash, and v dash, right, most of the time you need to go second order. Okay, so these are just algorithms and mathematics.
Okay, so we can start with the first order at this moment. Then later on, what we have to do is initialize the solution. So basically, the initialization is like to tell the solvers what are the, or allow the solver to have a very quick calculation based on your initial conditions and boundary condition. Okay. Okay, so the initialization is done, then we can run the calculations. So the number of iterations, right, is actually how many steps you want to calculate. So basically, you can key in any numbers, but the solver will actually stop while the solution is converged. So how we actually determine the convergence criteria? We can actually set it over here, the residuals. We normally set by default is 1 times 10 to the power minus 3, which is like the difference between the left hand side corners and the right hand side corners. Okay. So okay, then click calculate, then you will see the residual plots here is coming down. Okay, so when the exclamation mark is appears, then you actually means that your solution is already converged. Means all these variables here, like continuity, x, y, z, and the so-called turbulence variables, they have to be at least reach this so-called convergence criteria, which is 1e minus 3.
I want to say also, see, this solution is converged, right? Because of the settings that we set, right? You go back to the settings. So you see right here, right, it's all to power minus what? Minus 3, right? Okay, let's say I change this to minus 5 or minus 4, whatever, right? So now, right, if I do my simulation again, so I initialize again, and I run my simulation. Okay, you see that your convergence changes. Right? Does it change? Right, the number changes also, right? Because it's how you set the convergence, right? So this is up to you. Yeah. If you think that I only need this amount, it will be this amount. But if I need more, right? Obviously, if I do I do minus 6 because I want more accurate results. Okay. But then because the mesh is so coarse, I know right. No matter how I want to be accurate, you will have a certain number because it's a coarse mesh. Yeah. So then all these things will change. Understand? Okay, that's what we're doing.
Okay, so actually in another way, right, we actually can monitor some of the variables, like example mesh flow rate at the outlets, and then so when we calculate the solutions, the residual will start coming down, and then while we reach 1e minus 3 equals right. So we can actually monitor one of the variable like mesh flow rate and the outlets close iteration. So it will come down and reach a steady state. So if this solution is already converged, but your solution is just halfway here, means your result is still not yet the final result. So maybe you have to go to that particular windows to further reduce the convergence criteria to 1e4 or 1e5. So maybe meaning here is, example here is 1e minus 2, here is 1e minus 3, then here is 1e minus 4 and 1e minus 6. So which solution criteria you want to set? Basically, definitely it's not here, right? Okay, because it haven't reached the final solution. So maybe you can consider to use 1e minus 3 or 1e minus 4. Okay, so in your final year project, maybe you can try to plot this out and then label at what kind of residual convergence criteria you set and then what's the result. And then show that your solution is already so-called stabilized. So after the solution is converged, then the next thing is what? Post-processing, right, to get the result. Okay, so actually you can do the post-processing is this Fluence itself, or you can use the other post-processor which is at the workbench here to grab the results. Okay. So first of all, if you want to so-called get the control plots, you have to actually cut the plans. And then you will extract the result based on the plan and display it in colors. Okay, so firstly, we create a plane which is cut over XY plane, slide. Okay, so we maybe move a bit. To the center of the car, and then after that click on the contour, select the car, the plane as the locations because you want to display the pressure or velocity controls on this plane. Okay, so select the variables, maybe velocity, and then apply. Okay, then you will see this kind of plots. So, is this result good? Not really, right? Because the mesh is too coarse already, so you see those kind of very jagged kind of values. Okay, so next thing, maybe let's try to refine the mesh and then plot the results. Okay. So what we need to do is just to update the project, and the solver will actually automatically read the mesh again, calculate again for you. Then you can see slowly, yeah, the tick is forming just right beside the steps. Okay, so you no need to go in and reset again and do the calculation.
So do you see how fast it is? The moment you do your geometry correct, right? The mesh, you just click a button. Then you don't have to do anything else. Just need to wait, and then you go to this part, right? Then you set the solution. Okay, so it's the first step that are difficult to get the geometry and the mesh. Okay, the rest will be quite simple.
You guys see the difference? Okay, so just now this area is actually very huge, right? Then here is not that refined. Then maybe you can actually further refine the mesh. Like example, basically what is important for this kind of analysis, the vortex and the downstream drive. So if you want to resolve this, maybe you can consider to build one more volume that is covering these bodies and then refine the mesh here. Okay, so basically we call this method as a body of inference. Okay, then you're able to get very fine kind of features across this for the downstream. But visually, if you want to improve the plot, you can actually increase the number of control here to maybe 50, and you will get a smoother kind of plot. So this is to cheat the professor. Okay, so this is the velocity plot, and then you can actually switch to the pressure plot to compare. So basically, why here is higher static pressure and here is lower? It's because here is the emission points, right? So the static pressure is the highest, and then high pressure, low pressure, drag force performs. Okay. Okay, so this is how to plot the control plot. Oh, you guys see all my email already. Okay, so next thing we can actually create a streamline. Okay.
This one is all about you.
Then we can select which is the phase to start off. Normally it's from the inlets, so we just select the inlet, and maybe if you wish you can increase the number of points. You can see this kind of things, and you can create the animations. Then it will show you how does the flow is being so-called passing through these objects or your car. Okay, so this is the some of the so-called important steps for the post-processing. Okay, this is actually to cheat the professor also. Okay. Any questions so far? No. Okay, you guys want to try it yourself for this particular simple CFD simulation? We'll do it together.
Let's just try together. So you all can then we go for lunch.
This 15.0.
Huh?
16.5. Okay, so just now for the comparison between cos and phi mesh, right? Apart from observing the plot, the other way is maybe we can so-called extract a physical value like drag force. So meaning if you use cos mesh, the drag force of the car is maybe around 1 Newton. After that, you refine it to medium mesh. The drag force is 1.5 Newton, and then further go to the final mesh, it is about 1.4 something Newtons, 49 or something, which is very, very approximate to 1.5. So it means you can actually use the medium mesh for your applications. Okay. Okay, so maybe for your case, right, you can click on the start and then look for workbench 16.2. But for my case, it's 16.1. Okay. That's mine is slow. Okay, so next, you can see the analysis system here. Okay, then there's a fluid flow fluence. Okay, so click on it and drag and drop into this yellow colorblind, red color box. Okay. Get it? Okay, so firstly, again, we need to have the geometry, right? So let's double click on the geometry. Then, the dimension is gone. It's okay. You guys remember the values? Okay, so firstly, click on XY planes. Okay, then right click, click on look at, and then from here, we do the sketching of the so-called for the car, square car. Okay, so let's click on this sketching, and then scroll down by clicking this arrow bar here. Okay. Maybe for your case, you can actually see the rectangles. Okay, just click on the rectangles, cross your mouse over the origins, then you can see a P. Cross over to the origins. Just move your mouse over the origins, then you can see a P. Can you see? Okay, then once you see the P, just click the mouse button, left mouse buttons, and then make the rectangles. Then next thing is to dimension it. Can follow? Okay, now. Okay, so how to dimension it? So we have to click on the dimension button here, and then just click on this edge of your rectangles and drag it out. This side of the rectangle and drag it out. So we don't need to worry about the distance from these dimensions to your body because we are not doing the sketching kind of things. Okay, so what is important here is key in the correct values here. H2 is 2, E1 is 1. Okay. And then after that, we need to extrude this particular box. So click on the extrude button. Can follow? Okay, extrude, and then the geometry actually means this sketch. So we just simply need to click apply because it's already selected by default. Can follow? Okay, then we have to define the depth of the height of your cube. Okay. The box so it's 1 meter, this 1 meter, right? Okay, then click generate. Then you can actually see a 3D cube. Click on generate buttons. Generate. Here. Okay. Who cannot get the rectangular box 3D one? Okay, so we'll assume that you guys has already get the 3D flight controller box. So the next thing is to generate the big box in order to get the fluid volumes. Okay, so again click on the XY plane. Okay, then after that click on new plane, which you actually can find an icon here, new planes on top. Okay, just click on it, and then you can actually see the detail view of the plane 4 is appearing.
Yeah, the extrusion.
So the base plane is, make sure that it is XY planes, and then the transforms is offset global Z. Okay. So I will repeat again. Okay, so in order to offset the planes, right, we have to click on this new plane. Or you can actually click on create new plane. Follow?
Yes.
Okay, after you click that, the detail view of the plane is either plane 5, plane 4, or any plane. Okay, that is appearing here. Then the next thing is you have to define this particular plane is offset from where. Basically, it's the SY plane. And then the direction is transform or offset from global Z directions. This one, transform 1. Okay, follow? Okay, so after that, we actually have to offset it, go down by 4 meters. So just minus 4. Anything I can. Okay, so it's a rough value, just that it is big enough to so-called enclose these volumes. Then click generate. Okay, you can see the plane is being offset to the exact location that you need. Okay. So next, we right click on the graphic windows and click look at again. Okay, can you guys get the offset plane? Can So again, right click. Okay, I'll just continue. Okay, so next thing, after we get a new sketch and a new planes, right, we can actually click on the sketching again. Someone is on leave. Okay, then click on the rectangle again to create a big box. Okay. Maybe I repeat again. Okay, so after we get the plane 5, right, or for your case it should be plane 4 or something. So just click on that plane, and then you can see there is a sketching options here. Okay, this one. Okay, click on it, then click on rectangle. Then you can draw a big box to enclose your car. Okay. Okay. Then make sure that it is at the plane that you have created just now. Okay, right. Can I continue? Okay, so after you have this big box, right, what's the next step? Who can answer? Yeah, dimensions. So dimensions, right? Distance. Fast, right? Just I undo and redo again. Okay, so after you click on dimensions, right, then you go and click on length or distance. Okay. This one, length or distance, is actually one for the fourth options.
what thing?
Okay. So after you have clicked on this, you can later on click on the edge here. Maybe just follow together. Click on this edge. So that click on your origins, the x-axis. Then you get the dimensions line. Then again do it for the other edge. Okay? Can you get it? Okay, then next thing is the distance from upstream to your object and the distance from your object to the downstream. So you have to click on the upstream edge again and then do this particular axis. Okay. And next you can click on this to the downstream. Okay, so you guys can get this 4-dimension line. So I will just assume that you guys can get it and continue. Okay, so what is L3 and L4? 5 times of the height, right? So it's L3 is 6, L4 is 5, then L5 is 5 times 2 is 10, correct, bingo. Then what is the downstream length? 2 times 10, 20. Actually 20 is to plus 2 lah, it actually in more accurate a more accurate value because it's 10 plus your length. Okay, so it's 22. So after you have get this sketch with correct dimensions, right, you need to click on the extrude again. Okay, click on extrude, then you can actually see there is a gray colors, edges is fitting from your sketch. Okay, so for the geometry here, just click apply. For the operations options, right, add material means you are adding this particular sketch to your existing so-called geometry. So what we want to achieve is we want to add additional volume which is not interact with your car. So we have to use the option of add frozen. So please change the operation to add frozen. Okay, and then the height is 10. Just click 10. Generate. So we get this. Okay, yeah. So what is the next step? Still remember? Okay, who wants to answer what is the next step? Although no prize. Okay, we now have one big box and one more small box. The small box is your car. The big box is actually the volume that is going to be your fluid volume. But your fluid volume, we are not considering the structure itself, which is the car. So we have to subtract the big volumes to the small volume in order to get the fluid volumes. Okay. So how to achieve this? We just click on create, okay, on top, and then go to the bullets options. Okay, then you scroll this down, and then you can actually see two parts, two bodies, right? Click on the plus, you can see two bodies here. Okay, just prepare it first. Bullet. So for the operations, we change it to subtract. The target body is the big body. Okay, then the two bodies is your car. It's like making agar-agar, you need the more, right? And the liquid. Okay, so this is the procedure.
No
Okay, so do you want to preserve the car? No need, right? Because we only need the fluid volume. So we just leave the preserve two bodies as no and click on generate. So now you will get only one body, which is
not sliding.
a hollow body. Can you get it? Oh, it's actually at.
So you went to Boolean, right? Then you use subtract, then target body is outside. Two bodies are inside. Right, unsubtract. 它不是叫你刚那个多part two body，它那个手。
Okay, some of you actually after create the extrude, right, the small car is being eaten by the big box. So basically, it is due to you have to change the operation to add frozen instead of add materials. Okay, so who got that kind of error? Okay, so change the extrude operation options to add frozen.
Is it?
Okay. Okay. So after the extrude is solved, right? Then you need to have two bodies. One is the big box, one is the small box. Two bodies only, right? Then click on modeling. Get it? Then you check whether it's the bullet available. Huh? Okay guys, so if example you have okay, attention please. Okay, so basically if your model is ready, right, you can see a green tick beside it. So if you see a so-called the thunder kind of symbols, right, means you actually haven't clicked on the generate. So you need to click on the generate first in order to get all the operations ready. Okay. So if you have the thunder marks, right, means all these options cannot be used. Okay. So all of you have already get the fluid volumes. Okay, so I will proceed to the meshings. Okay. So those who have done the geometry, you just need to close the design modelers, and then you can see a green tick at the geometry at the workbench. So you may consider to save this so-called exercise. Save as. So I think you guys can create your own folder at the desktop. New folder, TAP, and then save it as workshop 1. Just click enter. Okay, so next we proceed to the meshing. Okay, so just double click on the mesh.
We create a build create target bodies two bodies.
Okay, so do we run the measure? Okay, so first of all, you click on the mesh. Okay, maybe let's try to just click on general mesh, see what happens. So is this kind of mesh good enough? So this is actually the default mesh. So in order to refine the mesh, right, you can click on sizing, change everything to 5. The smoothing change to high, and the transition change to slow. Okay. Then we click on general mesh again. Okay, so is the mesh getting final? Okay, so basically, when you do your FYP, right, you need to not only observe the convergent residuals to check whether how does the convergent limit affect your final result. You have to check the density of your mesh also. Like example, repeat what? Okay, so after you click on the mesh, right, change the relevant center to 5, smoothing to high, transition slow, span angle center 5. Just change everything to the highest span. Got it? Okay, basically it's the relevant center, smoothing, change to high, transitions, change to slow, all use the highest options. Then you actually get a final mesh. Okay. So since we have already got the mesh, what are the next steps? Can you follow? Okay, maybe let me repeat again so you guys have already get the geometry, right? Okay, after you get the geometry, have you entered to the measure? This one? Okay, so have you see this object? Okay, so click on the mesh and then change all the setting here to like relevant center change to 5, smoothing change to high, transition change to slow, span angle center change to 5. Fine. Okay, then click general mesh. Okay, then you can see a final mesh like this. Okay, so after you have got the mesh, right, you have to tell the solver like which boundary is belong to wall or inlet or something. So in order to do that, we have to give the name at that particular surfaces. So firstly, just click on the geometry first because the mesh is very irritating. Okay, so remember where is the inlet and where is the outlet?
So ours is one solid box. How to make it transparent? How to make transparent?
Color. Okay. Okay. In order to make it a so-called transparent view, click on the view and check on wireframe. View wireframe. Okay, can see a mouse box inside? You have to see a small box inside, or else maybe just now you have to redo the geometry. Got it? Okay, so next we have to name the boundary. First of all, we name this as inlet. Right click. Then there's the option is called create name selections. Then we name as inlet. Okay. Then the one which is further away from the object object is called the outlet. Okay, got it? Then all the four surfaces that is surrounding your body, you can name it as the wall.
Control.
Okay, so how are we going to select the small box inside so that we can name it as car? It's very difficult, right? Because when you select, it's always selecting the external geometry. Correct, right? Okay. So how to name the
Select all.
yeah, right click, select all, then deselect all the external body. I repeat again. So right click on the screen, click on select all, then every surfaces will be highlighted. Then next click on the control buttons and deselect the external boundary. So when rotate right, release the control. Then click on this and rotate again. So when every time you want to select the surface right, you have to click on the control button for multiple surface selections. Okay, so you now get only the internal surfaces to be highlighted, right? So right click and create name selections. Name it as car. Okay, can you get it?
It's a box, why is there a car?
Okay, so next let's check whether all the boundary is already named. Inlet. Is it same as mine? Outlet. Okay. The wall and the car. Okay. Okay, so after you have get all these mesh and boundary conditions defined, can you guys please right click on the mesh and then click on the update. Okay, so wait for a while, maybe 5 seconds, 5, 4, 3, 2, 1. Then minimize it and see is there a green tick beside the mesh. Okay. Got it right. So next thing, double click on the setup. Okay. Then let's use parallel processing for core. Okay, everyone can follow. Then click OK. Okay, quick questions. What solver should we use? Pressure based or density based? Oh, why? The speed is only 5 meters per second, right? So the Mach number should be 5 over square root of 5 over 330, is it? So it is actually, it will be less than 0.3 of Mach number, then it is a incompressible flow. Okay, so we have to use the pressure based solvers. Okay, after that, we can just leave everything as default here because we are conducting a steady state kind of analysis, and then we ignore the gravitational effects. Okay, then click on the next option, which is on the model. Since we are not conducting multi-phase or any thermal analysis, we will leave everything here as default, but change the turbulence solver to the sparse anomalous. Okay, so we just double click on the viscous option, change it to sparse anomalous. Okay, then click OK. For the material, right, basically actually we are using air, so we don't need to add any new materials here. But it is a good practice to go and check whether your control volume is actually belong to air. So how to check that? So click on the cell zone conditions. Okay, then click on edit. Then make sure the material is air. Okay, Then click OK. So what's next?
You just go to the cell.
Fluent database.
Okay, boundary conditions, right? Okay, so
I just
make sure your car is belong to wall. Okay, if you want to further check what's the conditions, right? Basically it is stationary wall, no slip conditions. Then click OK.
No.
Then the inlet. So it's a velocity inlet, right? Make sure you select velocity inlet. Then click on edit. Enter 5 as your magnitude. 5. Then click OK. Your outlet is pressure outlet. Double check whether your gas pressure is 0. And your operations conditions here is 1 atm. Okay, right? Then just click OK. Then lastly the wall. Check whether is it belong to wall. Okay. Then let's click on the solution method. Change everything to first order. The pressure should be changed to linear. Okay, then again for your FYP, right? Maybe you can compare across like these two different settings. You can run it with first order first and get the result, and then switch to second order to check whether it's the result different or not. If it is different by a lot, right, then you can consider to refine your measurements. Okay. Then next, click on solution initialization. Huh? Please follow.
Outlets.
Okay, let's go back to boundary conditions. Rewind back. Okay, outlet is pressure outlet. By default, it's pressure outlet. Then just make sure that the gauge pressure is 0, means it is discharged to atmosphere. Okay, click OK. You can follow all of the scanner.
the rest you can.
Car is wall.
Inlet is 5.
You need edit or not?
Inlet need to edit.
Inlet is velocity inlet with 5 meter per second as the magnitude. Okay.
Solid only. Wall only.
Wall I don't know. Wall I don't know.
So next thing, we have to initialize the solutions. Okay, just click on solution initializations and click on initialize. Make sure the option is under hybrid initializations.
How come it's value and value?
BC is on
Yeah. Okay, then click on run calculations. Input 1000 as the number of iterations and click calculate. Okay, you guys can get the things calculating.
Yeah,
Okay.
That's alright.
Yeah. Like that.
yeah.
Next steady state. So I'll change the conversion.
Okay, I think we'll stop here for a break, okay? We'll come back and then analyze the results. Okay, so you can go for your lunch. About 1:30 we'll come back here. Okay, so now we can help those who have problems, but please go for your break. Okay? Then we'll analyze the results later.
We just go. Why so many?